Jonathan Jackson. I work here at Hashrocket. I've been developing, just a little bit about me, I've been developing professionally since 2008, mostly in Ruby, always in Git, surprisingly. I've never really had a whole lot of experience outside of Git. And we're going to talk about Git's Plumbing and Porcelain. I chose that title for the talk because Git internally represents itself or references itself in the context of plumbing and porcelain. So just like in your home, you have plumbing. You have pipes underneath your sink. You have all manner of thing underneath in the walls, hidden away, that allow you to have running water and just basically just allow you to have civilization. And then you have more like forward-facing things like the toilet or a kitchen sink or any of these other things. And those things are designed to be interacted with by an actual person. So when Git talks about plumbing commands, it's usually talking about things that it uses internally to do things, to get things done. And then the porcelain commands are the things that users are actually designed to interact with. So that's what we're going to be talking about today. It's going to be kind of a whirlwind tour of a whole bunch of stuff. Hopefully it's fun. And it starts here. Do you know who this man is? It's Linus Torvalds. Did you know why he's... Why do you know him?
Well, he's inventor of Linux, but he's also inventor of Git.
He is. He is.
It's Windows, right?
Totally Windows. Yeah. Okay, so Linus Torvalds, yeah, he's the creator of Linux and later Git, and it's interesting. The existence of Git is directly tied to Linux, so they're kind of inextricably bound. Git was designed with the Linux kernel in mind, so I want to talk a little bit about the Linux kernel just to kind of give it a little backstory. So the Linux kernel is a really complicated code base. It has a lot of open source developers giving on all the time. So it's distributed, highly distributed, like all manner of people have contributed to it and dealt with this guy, who we'll get to in a second. So, given the kind of environment that the Linux kernel has to have to exist, it has to have a few things. The source control for it has to have a few things. The first thing is that it has to be reliable, because this is used, all over the world for very critical systems. It has to be reliable. You have to be able to undo changes to make sure that things can work. You have to be able to do all manner of things. It just always has to work. You have to be able to manage the project efficiently, and that's something that is really hard to do. For reasons that we'll get into in a little bit, so the source control has to have that. It has to have support for distributed development. So you have to be able to develop wherever you are. So since it's open source, you can have developers anywhere in the entire world. And then it has to have support for nonlinear development. And that's something that Git does really, really well for branching and coming back and handling merges and handling that style of development. All right, but first let's go through a history of version control. It is an interesting journey. We're going to kind of go back in time quite a bit, since I don't know. It depends on when you started with computers, but this has been a problem since the 50s and 60s. So what are the first things that come to mind when you want to version control something?
Good.
Git now. Well, the first thing, and what I was looking for, is files. Just files. I want to take a file, and then I want to append v2 to it, or a folder. Copy the whole thing and do it. And this is before VCs exist, but it also happens to people who don't know about version control. And to that end, I have an amusing story about my first Rails experience, Rails project. So I was developing a time management tracking application, and I was thrown into the deep end. I was not going to be paid until the product was delivered, so I had to do everything and from scratch, learning it myself. And before, obviously, I didn't know about Git, so I used a USB stick, and I copied the entire Rails directory into the USB stick as v2. It was awful. It was absolutely the worst thing I've ever done, and it's kind of the example of the first solution is not always the best solution. So, what are some of the pros and cons of using this style of system, this primitive style system. It's simple. It's really easy to do. It's very simple. So what are the cons? The simple is the only thing that's good about it. So some of the cons are going to be that mislabeling becomes, you have a human element. So mislabeling becomes an issue. If you were to mislabel a file, you could lose an entire file. You can override an entire version. There's no granular control. Your granularity is a file. So you can't really go any more granular than a file when you're just naming files. So it's kind of a bad idea for code. You can't do, I changed all of the method defs to use camel case instead of snake case. You can't do that. You have to change the entire file, and then there's no, like, I just changed these very few lines. So programmers being what they were, and this is, like I said, going back into the olden days. So programmers decided to build a system. And the system is local version control. And this is where you have your project files. And the project files can only be checked in and checked out via a program interaction. So you have to actually ask the program to check out a file, and you have to enter them in and get them in and back. And then the program itself internally will handle the versioning. And it's checking it out. So you can really only have a single checked out file at any given point in time, and that keeps you from overriding or mislabeling or losing data. So yeah, local versioning control. And let's talk about some of the pros and cons of that. This is an example of revision control system. It came out of Purdue in 1982. And one of the reasons why I wanted to mention that is both to date this style of source control, because it's old. And that's source control, code control as well. But RCS is also used as the under the hood mechanism for CVS, which stands for concurrent versioning system. We're going to get that in a second. Some of the pros for this, it's less error prone than writing a file, obviously. It accounts for branching. Both of these accounted for branching. Revision control system, I believe, used, there's a term for it, latest version with backwards delta, and the other one used interleave deltas. So it's just the changes from one commit to the next. Some of the cons for this method is that it takes place on the developer's local machine, which has some good and some pluses and minuses. It's fast, obviously it's fast, but you do have no real means to collaborate with other coders who don't have access to your system. So there's no real way to send it out there. Yeah, my notes have still pre-GitHub, which is pretty true. Okay. So programmers, being the stalwart servants of mankind that they are, decided to go with a new paradigm, and it's switched over to a centralized version control. Instead of storing the revisions on your local machine, they would store them in a database on a server. And the network here is not necessarily the internet. Sometimes it's just like a local area network or a WAN or any number of protocols. And this is where each user can check out files from the database and edit them and then check them back in, and then the next person can pull them down. You're not really supposed to take out more than one at a time. So like if user 1 has file A out, user 2 should not check out file A. And that leads us into some of the cons to this style, where merges are a nightmare, really difficult. Some examples of this are CVS, as we mentioned before, and that's built upon RCS. I think the last patch to CVS was in 2008, which is right around the same time that I started coding. That's not to say that it wasn't kind of fading out, the paradigm wasn't fading out, it was still used until then. Probably still used today, honestly. So some of the cons here are that since it's centralized, there's a single point of failure. So we've gotten past the point where we can't share it with people. Now we can share it with people, but if that server fails, then everyone is out of luck. You just lost your repo. There's nothing to it. It's gone. But it does allow for collaboration. So you can share code with people who are thousands of miles away or in your room right over there. And that brings us to the next paradigm, which is distributed VCS. And this should look familiar because this is basically the structure of Git. where you have users, each user has all of the version control system to themselves, and they have their own history. And then they can communicate with each other to maintain usually a remote that has like the canonical list of history. So some of the pros and cons for distributed stuff. It's offline access, so you don't have to have access to a server, but it doesn't preclude it doesn't preclude online access. So you can still save it to a remote and have that sort of communication. It has a focus on efficient branching. So one of the advantages of the LCS, the localized version control, or LVCS, was that all of the changes and all of the changes that you were able to do on the system were fast because it was file system level. So it was very, very fast. And that is true here as well. Because you're doing it all locally, and then you're communicating the differences and the changes with your other nodes in the distributed cluster. Merge conflicts can be handled at your own pace, and there's actually a mechanism in Git to handle merge conflicts, several mechanisms, in fact. So the cons to this, and there are quite a few that I'm not going to list, but 3 that I came up with off the top of my head are that there's some intellectual overhead. You have to learn Git. You can't just magically know it. You can't just dive into it. Some of the other systems you could also have, that con could be for them as well. There's intellectual overhead for any time you introduce some layer of abstraction, but it's exceptionally true for this. You can't check out sections of the project. In a lot of source control systems, you could check out an individual file or an individual folder and work on that and then send it back. But with Git, you have to download the entire project. For some people, that's fine. I think if you have like large binaries in your project and you're tracking them, that can become an issue. It doesn't track empty files. That's a con, but we'll get into why that's not necessarily a problem in a second. So here we are with Git. So we've gotten to all the way through the history, and now we're back to Git. And so yeah, in case you were wondering, Git is British slang for an unpleasant or contemptible person. So yeah, so he has kind of a sense of humor. He's also rumored to be a contemptible person. Yeah. All right, so once again, Git is tied to the Linux kernel. So let's go through a history of Linux kernel. This is mostly just because I thought this was interesting. So you may or may not. In 1991 to 2002, it was passed around. This is largely done through email. You would just email patch files, and then you would apply them to your stuff, and then that's how versioning happened. And that was actually kind of cool. You can still do that with Git. Even with Git, you can email patches and apply them. And then in 2002, they moved to a proprietary system called BitKeeper. This was a good deal. Richard Stallman had an issue with this because BitKeeper was a proprietary organization. So he had an issue with a proprietary company holding control over an open source project. And several Linux core maintainers shared his opinions. So this was a little bit of a controversial decision. And it was a distributed version control system. A lot of the ideas from BitKeeper were incorporated into Git. So that's pretty interesting. And then, so in 2005, this is the cool part. In 2005, BitKeeper's license was revoked so it was a proprietary piece of software, and Linux had free access to it, but it was revoked because this guy, who was a Linux contributor, attempted to reverse engineer the software so that he could build it himself. So in response to this revocation, Linus Torvalds developed Git. And he did so in 2 weeks. I think the initial release took like two weeks, less than a month. Yeah, so let's use Git. All right, so the first thing we're going to do is we're going to talk about the file status lifecycle. And I don't have any notes on this because I just wanted to spend some time on it. It seems really difficult to understand, but once you get through it, it's helpful to me anyways. So you start in the untracked state. And this whole cycle, this back and forth here, is basically when you initialize the repo. That's the dividing line. After that, you're going from an unmodified state to back to like through the process and back to an unmodified state. So once the files are in the system or removed from the system, they're just don't think about this section. Then you're in an unmodified state, and when you're in an unmodified state, you change the thing. So you edit the file, and that takes you to this modified state. And we're going to explain the process to get these through to these different stages and what Git internally uses to represent unmodified and modified and staged. So it edits the file, brings that to the modified state. And then to get it over here to the staged file, you actually have to do another action. The reason that this happens is so that you can group like changes together here. So you can edit like 17 files in this phase, and then only stage 2 or 3 before you commit that in. And that helps you keep like a unified history of things. You can track meaningful progress in your project by committing like files. So does that make sense? Does everyone? Yeah. Also, you can stop me for questions. Yeah.
Yeah, files can be modified and staged at the same time. When you try to commit a part of the changes you made to the file.
Yes, that is absolutely correct, and that's good. So, yes, if you stage a file, and that file changes again, the stage changes are staged, and that file is going to show up again in the modified state. And if you wanted to incorporate those changes, you would have to restage the file, and it would override the existing file. I'm actually going to get to that in a second. No, that's cool. All right, so let's start actually doing some commands. This one is how you initialize a Git repo. Don't worry, I'm not going through all of the commands that you have to use, just a few. And this is gonna build a whole. It's gonna build a .git directory, and then it's going to create a head file, and that just points to your master branch. But it's also going to do a whole bunch of things underneath that surface. It's going to create inside of the .git directory. It's going to create folders for objects, which is the object database, ref heads, which are for branches, tags, which are for tags, and then template files. And you never really have to look at those, so you don't really need to know about them. They're just kind of like, it's important to Git, but you don't have to actually interact with those things. But Git does a lot of things underneath the surface. Yeah. So it's really important to note that since we just initialized this, and this is getting a little meta because this is me taking screenshots of me staging this presentation. So yeah. So anyways, so you notice these are untracked files. This is my keynote that I'm actually showing you. So to actually stage them in, you have to do the next command. You have to add it. And this actually stages the file into the snapshot, into the next snapshot, or the index. Git will refer to these things interchangeably, snapshot or index. So I will likely use them interchangeably as well. Just know that they're the same thing. So here I am. I'm going to add this file in right here, and then I run git status. Git status will show you the information that you need to know about your non-committed changes. So anything that's been committed will not show up in git status. We use git log to do that, and we'll get to that in a second. Git status shows only non-committed changes. So it's staged. Yeah, and I actually have a note. Files added to the snapshot can still be modified. Pavel, looking at you. All right. So, and then when we commit it, this is the whole lifecycle that we just saw earlier, but kind of in a different diagram. Can you guys read that? No. All right. I will just. Yeah. So these are project files, and this is that command you just saw, git add. I add the thing, and then that goes down to the stage snapshot area, and I can stage as many files as I want here. And then when I commit, this will be just git commit, that exact command. It'll ask me to write a message. I'll write a message, and then that commit will be dumped into the history. Does that make sense? Any questions?
So in that very first diagram where you have the untracked, when you add the file, it doesn't go to unmodified, it goes all the way to staged.
When you edit the file, it goes to modified from unmodified.
When you add the file
and when you,
from untracked.
When you add the file from untracked, so that's when the file doesn't exist. If the file has not been tracked by Git before, it starts here. Once Git knows about it, once Git knows about it, if you make a change, it doesn't start here, it starts here. Because Git knows about it, so you don't have to do this step again.
But if you add if you call git add on an untracked file,
it goes directly to staging.
Yeah.
Yes.
Which isn't reflected.
Yes. Absolutely. Yes. That is correct.
You could refer it like adding changes to an empty file, because empty files are not tracked by Git. So when a file doesn't exist, it's the same thing as just like having an empty file. And when you add a file, it's like you making changes to an empty file. And then you can like stage these changes.
I think git add -p or -n does that, which is intent to add. It creates like dummy files so that you can do patches and stuff. Is that what you mean?
No,
Like
what I
GNAP
was
is
trying
the-
to say is that when you create a file,
Mhm.
and like Git doesn't see it because it's empty, and like when you add something to this file, Git actually starts seeing
Right. Exactly.
as changes. Like Git operates with changes.
Git operates with changes, but if it's not tracked on purpose, because if it was tracked, you would end up with like binaries and configuration files and ugly files. So Git forces you to actually manually say these files are going to be tracked, and then everything else is going to remain untracked. Does that make sense? Maybe? Okay. All right. Yeah.
The difference here, I mean, it's make from
Go back to the-
otherwise- no here.
Okay.
So when you commit,
Mhm.
you really send files to the server, but in Git not.
No, you do not. You're not. This is not. This whole thing is all local.
You need to push.
Yeah, there's a whole other set of commands for dealing with remotes. I'm not actually
Okay,
going.
I know, but I mean, so it's why I need to commit.
Mhm.
I mean, for me, it's like I'm done with this file for now, and it's not sending to the server.
Yeah. So yeah. So as we were saying before, I'm going to go back a little bit to the slide over here about this one. Which one is it? Yeah, this one. So if you remember, this is one user, and this is a user, and this is a user. But these could all also be remotes. They could theoretically. There's no difference between this and a remote. Like GitHub would be a remote. So this is what we're talking about, where like you're going to put it into your history, and then if you wanted to go to a different remote, there's another command for that to push. But each one of these is a fully functional version control system without knowledge of the rest of the world. And you have to use a different subset of commands to actually interact with other nodes. And that's git push and pull, basically. So you would you do git remote add an origin. I think by default, if you clone from GitHub, it will create an origin remote. And then you can just push and pull from that. And that's what most people's interaction with Git remotes is. But the stuff we're talking about so far has only covered this section, just like one user's
And
interaction.
it's just like you wanna keep control, but only for you.
Exactly. Exactly. And then if you wanted to bring it into other places, that's when you would do like merges, and you'd have to deal with. So if we both modified a set of commits, we would have to deal with making sure the history could line up in a shared branch. So that would be a merge.
Is that Cat the CEO of BitKeeper?
Yes. He was so mad. And then yeah, he's back to it. Cats don't look mad. They're mad though.
Well, he just didn't seem very smart. Knocked his copy over.
Well, no, he's doing it on purpose. He's swatting
Oh,
it.
he's shoving it.
Yeah.
Cats don't drink coffee. They will
Please
not
shut
copy
stuff
cups
all the
over.
They do not copy cups over. That's absolutely true. Okay, so yeah, so this is the git commit. This is like what a file would have to do to actually get into the system. And this git add would actually work for untracked files as well as modified files. So this structure is what you would actually end up doing. There's only two commands that you end up having to do after you've edited a file or touched a file, which is git add and then git commit. And you can do some things with git add to make it more granular. So this looks like you can only add just an image. And for an image, it wouldn't make sense. But if this was a text file and you wanted to change just sections of it or patches, you can do a -p flag to add, and that would let you stage individual sections of the file. So you get much more granular control than just a single file.
Oh, Jonathan,
just mentioned something about binaries, but this is just for source code, right? Or do you actually put compile code in this?
You can store like anything with Git. You can store QuickTime videos or this or anything, but it doesn't handle like binary diffs. So you can track them so that you would have to do something. It would track the differences, but it's not going to let you do that fine grain. You can't like patch a file like I was saying. You wouldn't have more granularity on those files than you would it's just a new file or a different change.
But if you had an image or something like that, you need to just store it.
You don't have to do a different name though. It would still track the changes in between the files. You just couldn't stage like I want pixel quadrant this to be different, and that you would have to change the entire file, and it would just represent a new blob. But it would only represent that if it changed, because Git stores everything with checksums, and we'll get to that in a second. Okay, so this is how you actually view your commit history. So this is kind of a paired command with git status. So git log will let you see your commits, only committed changes. You can't see your current working directory. And git status will only show your current working directory, so they're kind of they're match paired. So you'll notice git log, and you're going to see this again. This structure looks very, very familiar. This will look familiar in another slide. It has a commit, and this right here is a SHA. It is the checksum of this commit's changes. And what that enables Git to do is to ensure data integrity. So if the file were to change even a single bit, the checksum would be a different, would look different. So Git would actually know about that. So if a file gets corrupted accidentally, Git will complain and say, hey, you have a new file. Like this is not right. Not that happens super often, but if it were to happen, you would at least know about it. It also does some neat things with for memory saving in there. And then it has the author and the message. You can do this. The git log accepts like a tremendous number of like customization options. You should take a look at .matrix at some point if you want to see the real extent of how customized how opinionated people will get with the git log. You can make it one line. You can make it show only these first 5 or 6 characters. Only show like the email, not the actual author. Any number of things, different colors, everything. So it's really useful. We use it all the time. It's very important. This is how you're actually going to use Git, pretty much. Okay, so now that we got kind of the basics out of the way, first off, do we have any questions? Questions?
Just use a Dropbox just to double backup.
I do use Dropbox, yeah.
It's like
it's so that my computer blew up before I pushed it to a remote server. I would still have it somewhere. Do you use Dropbox as well for that?
Not like this. I mean, it's just for normal files.
Normal files.
Not coding.
Yeah, I think I do. Yeah, I do it just in case of random failures. I actually don't think this repo for the keynote is actually pushed up because I had it in Dropbox, and I was like, I'm not going to push this to GitHub because it's already saved somewhere.
Yeah, it's different than just push all day, every day, because I don't have Dropbox, so it's.
You push the Git.
Yeah.
Yeah, definitely. Yeah, that's how we develop internally into Hashrocket as well. All right. So let's talk about Git's internal representation a little bit. There's 4 types. I only have 3 listed because tags are basically commits, just glorified commits. There are trees, commits, and blobs. We're going to talk about each one, but the first one is going to be commits, which is out of order because I changed the slide order. This is a commit. This is all a commit is. There's no mystery. There's no secret sauce to Git. A commit just references a tree object, which we're going to talk in a second, and then it references its parent commit. So that's how you keep that nice stack of history that you saw earlier, where you have C1, C2, C3, because it stores the reference to its parent. On the initial commit, this parent field will just not exist because that will be the root of the history. And then it stores the author, and then the committer, which I guess can be different things. And then a message. Yeah. So let's talk about trees. All right. So trees are Git's representation of snapshots. I mentioned earlier that they're also interchangeably used or referred to as indexes. So the snapshot area that you saw in an earlier diagram is basically a tree, and it's the current working directory as it stands at the time of the snapshot. So if you had a Rails project, it would be every folder and file in the project. That's not get ignored. It has no notion of time or author. All of that's done in the commit. So trees and blobs are both tied together with the commit.
What is the actual data structure of a tree?
Of a tree? I'm going to show you that in just a second, but it looks very similar to the output of tree from the Unix command, if that makes any sense, where like trees and blobs will be lined up, and then if you go into that tree, it will eventually terminate, no matter how deep the folder structure is, in a blob. And yeah, and we'll get into blobs in a second. And this is made meaningful with the commit object, as we mentioned earlier. All right, so I am going to do some demos. So if you have questions, you should probably ask them before I start doing crazy shit.
When you say representation of snapshot, and then later on you said that blobs are at the leaf, so it's actually just the metadata about the snapshot, not the actual data?
No, it's the actual data.
It is.
The data is actually stored in blobs, though. And trees are only references to other trees / blobs, and then the blob actually contains the data. So you go down the tree structure, and you'll go into all of the directories. Like each one will have a tree. Every folder will have if a folder contains another folder, there'll be a tree, and then whatever in that second folder, that will be blob data. So it's just kind of trees out fans like that. All right.
So,
Yeah.
So what would the commit reference? The head of the tree or the number?
It references the tree's identifier, which is a checksum of the tree itself. So yeah, tree, everything's just a file, and the way that it's all referenced. So a tree has an object identifier. A commit will also have an object identifier. So if you're looking for a specific commit, it'll have a SHA that's associated with it. And that's true of trees, and blobs even will have identifiers. And those are all just the checksum of that particular data structure. So you can actually recreate if you don't know the if you don't actually know the object identifier, you can calculate it with a git command and to retrieve it. Although it would never be lost. So yeah, so this is a little bit more like a diagram that kind of expounds upon it. So you have the tree objects. This is interesting. Trees can only be associated with exactly one commit. So in trees will contain trees or blobs. So down here, you're going to have a bunch of fanning trees and blobs, and they'll all terminate with a blob.
Can I?
Sure.
Go ahead.
No.
So if a tree can only be associated with exactly one commit, and a tree's SHA-1 is a hash of all the content of the tree, there's no concept of time or the author.
Right.
And what happens if I commit a file, and then in the next commit, I remove that file, make other changes? So I'm taking the tree from state A back to state A.
Right. So
It'd be
each
the
tree
exact same tree.
is the entire working directory. So
Right.
if you were to commit it in C1, and you were to commit a file here,
Yeah.
and then you do a commit and commit 2, that removes that file.
Yeah.
That file will still exist inside this tree.
Right. What I'm saying is then if it's C3, I add that file back. Then C1 and C3 are pointing to the
No,
exact same state.
they'll point to, if the SHAs are the same,
Yeah.
they'll point to each other. They won't duplicate the data.
Okay.
Is that
So
what you're
then
asking?
It would be associated with multiple commits in that case. 'Cause it's the same tree.
Yeah, the tree structure. Yeah, maybe.
Okay.
I'm trying to think of a clever way out of that one. It's not really the way. I mean, I'm talking specifically with regard to the way the commits lined up. That tree, there will only ever be one tree field in the commit itself.
Okay, gotcha.
Yeah, that's what I mean.
Okay.
You're right. They are going to self-refer where the blobs, especially with blobs, because the blobs is the actual data. So if there's multiple files that have remained untouched, Git won't just recreate them for each tree. It'll point to the ones that already exist. That's a good point. Thank you. All right, so blobs. Blobs are how Git stores data, file data. This also has no metadata, no file name or anything. It's just the object identifier. And if you're at all interested in the way Git stores the objects, they have the SHA passwords, or the SHAs, I guess. And the first 2 digits are made in that objects database that I mentioned earlier, in .git. The first 2 digits will be a directory, and then inside of that will be the remaining thing as a file name for the blobs. And trees and everything else. It's just raw data. Yes. Okay.
So just to clarify, it says blobs actually is the physical files, and the tree is like only the hash reference for this data.
Yes, exactly. So the tree will be a folder structure containing trees, and the trees will reference either other trees. So it's a snapshot of a directory, of a working directory. So the trees will represent every file as a blob, and every folder as another tree, and it'll reference another tree. Does that make sense?
Basically, trees are directories and blobs are files.
Yes, that is a really good way to put it, yes. It's very Unixy in that way. So if you know Unix, it's very, very similar. They map really closely together.
Okay.
So, yeah. And they're identified solely on checksums. So they're listed in trees. There's also trees. So this would be if there was a single folder, and then that folder contained 3 files. So as we were mentioning earlier, the blobs, since they're based off of checksum, they will only create new blobs if the file has changed from a previously modified state or previously committed state. And otherwise, it'll just reference that SHA. So this is one of the things that makes Git so fast, because it's only storing the changes from one commit to the next, not every file every single time. It also is one of the reasons why branching is really cheap for Git. Okay, so any questions? I'm not done yet. I got some examples for you guys. Any questions? All right. This is code, kind of. All right, so I went through this earlier today, and how many of you guys have used Git professionally? Yeah? Okay, cool. So you guys, this might be a little bit of review. So one of the criticisms I had when I practiced it earlier is that I kind of like went a little too fast. So I'm just going to go through a normal workflow a couple times. So I'm going to run git init, and this is going to create a I don't want to actually repo my, let's make a directory first. Test git. All right, so there's nothing in it. I'm going to do git init. This is going to create the .git directory. And it has all that stuff, which is cool. Now I'm going to make a file. All right, so now my prompt shows some stuff about Git. So the plus sign means there's changes, but I'm going to run git status to show you. So now there's an untracked file for a new file, as you can see. That's untracked. It's not modified because Git has never heard of that file before. So we're going to tell it about it. And say add new file. New file. Tab complete. So now if I do git status, I'm sorry, I don't want to, if I do aliases, call me out because, yeah. So now you'll notice that it's in the staged section. And then what we're going to do is we're going to commit. This is going to prompt me added some new file. All right. So we just committed it, and if we do git log.
Yes.
What happened?
Git status.
Oh. Sorry. Yes. Git status. I'm going to clear after each command. All right. So if we do git log -- one line. I don't like the full git log. We'll do the full one because one line is whatever. Yeah. We get this. We get our message. We get the commit that was created. All that stuff. And I'm going to add another file because, like I said, I went too fast earlier. So learn my lessons. Let's create a new file. Oh, yeah. do another. Ah. Does anyone see what happened here?
Yeah, you had the exclamation before.
Ah! No hooray for you. All right, so I created a new file. I'm going to add it again. I'm going to clear. Hold on. I'm used to having a little bit more screen real estate. Git status. Add. This is another ntrack file. Git add another file. Git commit. Did some stuff at a presentation. All right, so now that once, oh my God. Thank you. Yeah. I'm learning. All right, so we're in clean working directory again. And if we do git log, we have 2 commits now. So that's the general workflow and how you actually add and commit a file. It's pretty straightforward. All right, so yeah, I know. I'm gonna echo blah. I'm gonna show you that it's the same for modified files. So now I'm gonna have a modified file. So new file already existed. So when I appended blah to it. So now it's modified. It's in modified state, and then the same thing works here. So it's git add new file, and then git commit another commit. And this is how you work with Git usually. It's pretty straightforward. Git log. And now we have 3 commits. So each one is showing what happened, what we did.
I mean, so it's just git log shows only the commits all, or only you did before the last push.
It will show you all of the commits.
And there isn't any shortcut to show only the commits from last push?
From last push? I don't actually know. You could do something like git, what is it? Hold on. Yeah, git tree.
Git tree is also in ls.
Huh?
Git tree is also in
Damn
ls.
it. Is it git alias? How do you find an alias for an alias? Whatever.
No, I mean, whatever. Just
Anyways, you can get a nice pretty thing that'll say where head is, which is your current where you're at, your current current directory, and then it'll show branches in the log. And if you do that, you can see like if your head is 2 commits above master, that means that the last push it'll like whatever branch master is on, that's the last time. Not master, origin master. So like a remote branch, like say GitHub. If it was GitHub, this would be origin master, and you would know that the last time you pushed would be when you saw that, like the commit that line is on. And can you find out the alias to that? Thank you, because I would really like to know that. Sorry, you get used to a lot of these aliases, and then it's just all up in smoke from there. Okay, so now I'm actually gonna do the cool stuff. I'm going to echo blah into new file again. This will modify it. Sorry, git status. So it's modified. Instead of doing the old thing, we're actually going to use some of the plumbing commands that Git uses underneath the hood to make things work. Okay, that's awesome. I will print it out in a second. Okay, so we're actually going to do git update index. And then, so update index is a command that Git uses internally. This is a plumbing command. So this is the first one. We're actually going to do the exact thing we did earlier, where we just added a file, committed it, and flushed it to the log. And we're going to do it with only plumbing commands. This is not something you'll do on a daily basis. New file. Okay. So we updated the index with new file. And if you do git status, it's in the snapshot phase. So we're going to, so the commit is comprised of these things right here. Tree, parent. That's pretty much all you need to actually make a commit. So we're going to craft a commit. The first thing we need to do is git write tree. And that creates a tree object. This tree object took this snapshot. This is in the snapshot area. It took that, created a tree for it, and gave us the SHA. So now I'm going to do, this is the cool part.
So write tree by default creates a tree from the snapshot, not from your work.
From the index.
From the index.
Yes, absolutely. So one line. I'm doing this because we're going to need to reference the parent commit. So we're going to add another commit after this one. So I'm going to copy that.
One more question.
Sure.
So when you say that you're creating an index, is that creating an index at the head?
Yes.
Okay.
Yeah, it's based off of whatever your current head is. So if you change branches, theoretically that's not always true. You can be in a detached head state, which means that head would be on a different commit than attached head state. Yeah, so it'd be a dangling commit. You'd have a commit that's not associated with a branch. Yeah, I think that's what it is. Okay, so we have the tree object, which we're also going to need. So I'm going to copy that. You don't have to copy all of it. You only have to copy up to where it's unique. I think it's like 7 digits or something. We're going to do commit. Is it commit tree? Okay, so we're going to commit tree. We're going to pass it the tree object that we just created, right there. And then we're going to pass the -p flag. This stands for parent. So it's saying we're going to commit this. We're going to actually build a commit object. And this is the tree, and the parent is here. All right, so it looks like it just blew up, but it didn't. It's actually waiting for a message. So it's waiting for me to tell it what the commits message is. So I'm just going to say this is another message. But if you press enter, it just lets you enter because it doesn't know that that's a termination character. It doesn't know that that's what I mean. So I have to actually press Control D, and that's going to actually send the file exit. And now this is the commit object that we just built. So we can actually use some internal introspection or reflection methods to see that. So that's what the commit that we just built, which is like all the information that you saw earlier, and then this big giant message that I pressed enter too many times on. So that command, by the way, can be, you can look that up. It's git cat file. Git does some things underneath the surface that makes file reading difficult sometimes, and it's to handle some weird cases. So you have to use this tool to actually view the files that you want, and you have to specify the type. So you can do commit or blob. And if you want to do a tree, because trees are stored in binary, you have to do ls tree. Those are commands that I'll have on the last slide, I think. So we have this commit, and it's in a detached head state. So git log, I think. Yeah, it's not actually going to show up in the history because master doesn't know about it yet. So we actually have to update the master branch. Do I have that commit still? Yeah, okay, good. So we have to do echo, yeah, there we go, into, and this is the fun part, right? So git refs heads master. So we're going to override this file master to point to our new commit, and that's going to actually add it to the commit history. All right. There we are. So now it's at the top of our history, and that is the equivalent to this command. You know, message, whatever. This is a message. So all of that plumbing stuff that we did is this porcelain command. So I guess yeah, go ahead.
So you updated master. Do you have to update head as well, or does that somehow come along?
Head will point to whatever branch. It points to the branch name.
Okay.
Yeah. Yeah. So the abstract of this talk. I don't know if you guys read it. It was on meetup.com. It talked about when to use porcelain commands or plumbing commands, and the answer, I think, as you can see from what we just did, is you just never use plumbing commands, like ever, because it's a super waste of time. So yeah, you don't really want to use them except for when you're scripting things or building programs that interact with Git. Underneath the surface, they're much more simple. They're easier to parse because they are usually only going to print out the very minimum thing that you want or need. So they're great for scripting, but yeah, humans do not want to deal with that. Absolutely not. Yeah. So okay, I want to recap this because all right. Does anyone have any questions on this?
What was the file that you modified, that you that you put the SHA into?
It's .git slash. Oh, actually. Yeah. .git. It's inside the ref's heads, and then this stores all the branches. So if you ever want to know what SHA your branches are, you go there. Yeah.
Can you show what actually went to that tree we created? Like what?
Absolutely. Yeah. Do we have the tree object? We can get it. Git. Cat file. All right. So I'm going to cat the file, the commit file, and I'm just going to pass head because it's head now, which is our thing. And then this is the tree. Oop. All right. Sorry, I've been having copy and paste issues all day. Okay. So I'm just going to take that tree SHA, and then I'm going to do cat file ls tree, and then the SHA, and then that's what it looks like. So if I built a folder in here, so these are both files because I built files. They're blobs right here. If I were to have a folder in there, there would be a tree. There would be a tree, and then you'd be able to ls tree on the tree inside of this tree, and it would show you trees until you got blobs.
So where did our change save
from? So the blobs actually are the raw data. So if we actually we can inspect this more.
Of a file, or is it just
it's this cat file. It's the raw data. Blob. Yeah. So it's the actual file information.
So it's gonna save the whole copy of the file. It's not saving the diffs.
So if this file is unchanged and it's still in the next commit, it will only point to that pointer. It won't recreate the file. So if this was like 2,000 or 3,000 lines long, it was really difficult. It wouldn't copy it if it didn't change. It would only do the diff.
A large file and you make small changes to it, and you keep committing it, it's gonna keep copying the whole file.
Mm-hmm. Yeah. Do you have a question?
No, it's
all right, cool. Any other questions? So those commands were update index. I'm gonna. If you want to write them down, it's update index. These are all prefixed with git. Write tree, and then commit tree. So that's the equivalent of git add, and then commit with a message in tutorials. But you have to do a whole bunch of stuff. Okay. Yay. I don't know where I put the pointer anymore.
okay.
Yeah, right? All right. So, okay. So I'm basically done with the talk, but I want to talk about a few more things really fast that are not necessarily part of what we were just doing. So these are the references I used. I really recommend using RyPress. This tutorial, a lot of the examples that you saw, including the demo of the updating of the index in the plumbing commands, is appropriated from that. ProGrit is an amazing book that is free online. You just go to the website and just check it out. Just type in ProGrit to Google, it'll be the first result. So those two resources I relied on quite heavily. But then I wanted to talk about how you can actually do research without actually having to go online, or if you're curious about a command, there's these two commands right here: apropos and what is. And so apropos allows an arbitrary string, but what is requires the exact file or the exact string. So I'm going to show you what that looks like. I know the font's small, but you'll see why in a second. So if I do apropos get, and that accepts, like I said, an arbitrary string, it'll show me the man pages for all of the things that contain in there's an actual what is database. It'll show you a brief description of what a tool does and then where the man page is located. And what you can do with this is you can search for things. Update index is in here. A lot of the commands that I was not super familiar with are in here, and you can just say you want to look at the get index one. You can do man get update index, and it'll show you the man page. And these things are incredibly detailed. I'm sure you guys have ran into man pages in the past, obviously, but with Git, it's very well documented. A lot of the tools are documented, and especially with flags that you want to do, there's tons of things. And that apropos command works for other things too, like networking. It'll show me all the networking things or whatever. So I wanted to throw that out there. It's apropos or what is. Yeah, thank you. This is all my information. You can write that or whatever.